Unmute myself. Okay, so today we are going to look at, uh, well, from now on, we're going to, again, we are building on everything that we've learned so far. So we'll look at three different analysis techniques going forward. And those three techniques are node voltage analysis, mesh current analysis, and superposition, the principle of superposition. Typically, I cover superposition after I am done with node voltage and mesh current. But earlier this quarter, I realized the best place to cover superposition is right after we finish series parallel equivalent analysis. Okay, series parallel equivalent analysis. And the reason for that is superposition principle is built directly on this technique. Okay, so superposition principle basically states that if you have a circuit with multiple sources, before I state that principle, in this technique, series parallel analysis technique, we reduce the circuit down to one single resistance and we apply Ohm's law, right? So what if we have more than one source in the circuit? We cannot use this technique then. Or if it's not possible to reduce a resistor down to one single resistance, right? You might have two voltage sources, you might have two current sources, you might have three voltage sources and two current sources, you might have hundreds of sources, who knows? So then it's not possible to apply this technique. That's where superposition comes into the picture. With superposition principle, what we do is we take a large circuit with multiple sources and we break it up into individual pieces. We analyze the circuit with only one source working at one single time. Not one single time, but one source acting or working at a time. Okay. Effectively, we only have one source in the circuit and then a bunch of resistors. All the other sources are deactivated, or in technical terms, we reduce it to zero. We reduce all of the sources in the circuit to zero. We analyze the circuit using this technique, right? So you have a large circuit, you break it up into different pieces, different parts. You analyze each part independently. Each part will only have one source acting at a time. Then you have a result from each analysis. You add up all of your results from each independent analysis, and you have your total response for that circuit. Okay, so you have your total response for that circuit. So if you have multiple sources, we cannot use this technique, right? And so then we apply superposition. And then we apply superposition. So superposition, I realized early on this quarter when I was going over chapter 2, is that it will fit best right after doing this technique because it builds directly on top of this one. So let's get to superposition. If you have a circuit with n number of sources, doesn't matter what combination of voltage and current sources, but if you have a circuit with n number of sources, then the voltage or current appearing in any point in that circuit is a result of all those n sources working together. Okay. And so when you perform your analysis, you can say that the total response at any given point in the circuit can be a sum of all the component voltages and the component currents. I'll explain further. Let's say, well, let me explain using an example. Let's say you have a circuit with 10 resistors and 2 voltage sources. You got V1, you have V2, and you have 10 resistors in the middle. You need to find the voltage across R5, let's say. Okay, R5. Then you analyze a circuit with only V1 active. V2 is 0, right? It's 0. You find voltage across R5 due to V1. Then you reduce V1 to 0 and you make V2 active. Then you find voltage for R5 again. You have result from V1, you have result from V2. So VR5 has now two voltages. You add up those two voltages, you get the total response or the total value of VR5, that one single resistor. Does that make sense? Right? What is the obvious disadvantage? Think over it for a little bit. V1, V2, one analysis, two analysis. What if you have V1, V2, V3, V4, V5? Now you have 5 different analyses to perform. If you have 10 sources, you have 10 different analyses, and that is to find only one quantity. Only one quantity, right? If I wanted to find voltages for all 10 resistors and I had 5 sources in there, then it's 10 times 5. I need to perform 50 separate analyses to find the resistor voltages instead of just analyzing it twice, right? So that's the obvious disadvantage. It simplifies a circuit. It makes it very, very easy to analyze, but it's very time consuming. It's very laborious. So it makes sense to use superposition if you have like 2 or 3 sources, maybe even 4. But if it gets to like 5 sources and more, then there's no point doing it. Depending on how many quantities you need to find, of course. So if you need to find more than 1 or 2 quantities and you have more than 4 sources, then it's a highly inefficient method. For all other scenarios, superposition is an excellent choice. So how do we analyze only one source active at a time? Well, we do that by reducing all the independent sources to 0. Okay, again, remember, we only talk about independent sources in this class, right? Dependent sources, cannot be reduced to 0. So we won't even talk about those. Okay. So we reduce the independent sources to 0 by replacing a voltage source with a short circuit and a current source with an open circuit. And I will explain how and why we can do that. Okay. So we reduce the sources by replacing, we remove the voltage source from the circuit, we remove the current source from the circuit, and in its place, we put something else. And we'll see how and why. So reduce a source to 0. Let's look at voltage source first. Okay. Let's say you have a voltage source connected between terminals A and B of the circuit. Call it Vs. If you remove Vs from the circuit, how can we obtain 0 volts between A and B? The only way that the voltage at points A and B would be the same, would be 0, if both of them are the same exact electric potential. If there's a difference in potential, there's a voltage, so there's a voltage between the 2 points. But if both points are connected together, then they're the same exact electric potential, and thus we can say the voltage between those 2 points would be equal to 0. So we remove the voltage source from the circuit and we replace it with a short circuit, or SC. And that's why we replace a voltage source with a short circuit, to reduce it to 0. When you perform this replacement in a circuit diagram, all you need to draw is a wire. That's it. You simply draw out a wire, and thus you now reduce the voltage source to 0. Make sense? Right? And the same principle applies to current source. If you have a current source connected between points A and B, The only way that the current between A and B is equal to 0 is if there is no pathway for the current to flow through, right? Oh, there should be an arrow. So A and B. Place it with an open circuit. When you're redrawing this in a circuit diagram, all you have to do is remove that current source. That's it. Basically, replacing a current source with an open circuit effectively just means you remove that current source from the circuit. That's all. Doesn't mean anything else, right? So then you redraw the circuit after you have replaced the voltage source and the current source. Your circuit now changes. So think over it. Let me know if you have any questions. Any questions at all? So that we can apply the superposition principle. I will explain next with like 2 examples. But does this make sense? How and why we do this? So you have to remember voltage source, short circuit, current source, open circuit. Let's take a look at 2 examples. The first one, I'm going to show how we redraw circuits. And the second one, we will actually analyze the circuit and find the values. Okay. So example 1, and this was again a random circuit that I drew out earlier today. We have a voltage source, a resistor here, resistor here. We have a current source here. Another resistor here. Another voltage source, resistor. Okay, let's call it VS1, VS2, and IS. Resistor numbers don't matter right now. Again, this is just an illustration of how we would set up the circuit if we wanted to apply superposition. So as you can see here, we have 3 sources, VS1, VS2, and the current source IS. So when we perform an analysis, the first thing we want to do is, first of all, look at all the sources that we have in the circuit, right? So we have sources VS1, VS2, IS. So we analyze 3 times. Once for VS, second time for IS, the third time for VS2. Sorry, VS1 and VS2. Then we redraw the circuit diagram with only VS1 active. The others are turned to 0. Then we draw a second circuit diagram with only VS2 active. The rest are reduced to 0. And then only IS active, and the rest are reduced to 0. So 3 separate circuit diagrams. Let's take a look at VS1 first. So if VS1 is active, VS1 is active, what happens to the current source? It becomes open. What happens to VS2? The short circuit. And now the circuit has changed. So you will see this over and over again going forward, like chapters 3, chapters 4 especially. There will be like switching actions. There will be a switch that is flipped. It changes position. It might go from on to off, off to on. It might go from position A to position B. And the circuit will change. When the circuit changes, you redraw the circuit. You always redraw the circuit. Then you redraw it one more time, as many times as you need, until the circuit starts to make sense to you. So in this case, of course, we don't need to redraw it further. And we're not going to analyze it, but a quick glance at the circuit tells us that because of the disconnect here, these 2 resistors are effectively removed from the circuit, right? There's no pathway for the current to flow through. So there's no pathway for the current to flow through. These 2 resistors are basically redundant. But that's only true for this circuit, not for the entire circuit. We are analyzing this as if it's a completely separate circuit. And then all we are left with is VS1 and two resistors in series. Right? So that was VS. Yes, go ahead. And these two would be zero. Like there's no voltage or current over there, so it'll be effectively zero. Yeah. Any other questions? Okay, so let's move to VS2 active. And when VS2 is active, we have the exact same scenario. We have voltage source active. Current source is still open, right? And this time the disconnect is on the other side. OC, OC, SC, and SC. What do we see here? There's only one source and it's not connected to anything, right? There's only one source in the circuit. VS2 is active, but because of that current source in there, which is now an open circuit, there's nothing. Effectively, all the answers or all the voltages and currents in the circuit effectively zero. Again, we are not analyzing, but again, a quick glance tells us that VS2 is not contributing anything. But when we get to IS active, when IS is active, VS1 is a short. We have a resistor here, a resistor here, current source, resistor, voltage source to the short. And we can see now that there's a current source and four resistors in the circuit, right? Current source and four resistors in the circuit. On the far side, on the right side of the current source, we can see that the two resistors are in series because of the short over there. On the left side of the current source, we can see these two resistors are in parallel. Again, that's just from a quick glance. We are not analyzing it beyond that, but we can see how the circuit has changed, right? VS1 is here, VS2 is here because of the short. The resistors are now in series and in parallel with each other. We can reduce it down to one single resistance and analyze using those techniques. But does the procedure and the setup make sense? Right? Three sources, three separate circuit diagrams, three separate analyses for one single quantity. If you need to find two quantities, then 2 times 3, three quantities, 3 times 3, and so on and so forth. So it just becomes exponentially longer and longer and longer. Right? Any questions? Anyone? Yes. So whenever we have more sources, again, it's like it's another tool in our toolbox. So it's up to you as an engineer, as a student, to decide when you want to choose this. Now, if the question explicitly states use superposition, then you use superposition. If there are only two sources in a circuit, sometimes it's my like default analysis technique. If it's like 2 or 3 sources, I would straight away apply superposition. But that's just me. Unless the circuit's like super easy with 3 sources, and I would just like analyze as it is. So it's up to you as an engineer, as a student, to decide when and how you want to apply. All right, you and then you. Yes, voltages and currents. So we will look at current in the next circuit, but it could be any quantity. Yeah. Yes. Uh-huh. This one, right? Okay. Yep. We would have to add it up. And we'll see that in the next example. Yeah. Yes. Uh-huh. Yeah, VS2 is effectively not contributing any voltage or current to the circuit, but it is contributing a short circuit in the third one. So it's still important. We cannot completely ignore what VS2 is doing. Yeah. All right. Any other questions before we move on to the next example? Okay. All right. So here, look at the problem in its entirety. As an engineer, I always try to teach students, like as an engineer, you should look into every single detail. So when you're trying to solve a problem, look at not just the problem statement. You look at the circuit diagram, the illustration, graph, chart, whatever is given to you. Extract as much information as you can. In here, the critical piece or critical piece of information is this current direction right there. If you miss that, your answer is going to be incorrect, and you will see how and why. So let's read out the statement first. Determine current I2 using the principle of superposition. So you have to use the superposition technique. Current I2, locate current I2, which is on the far right of the circuit. Values for the voltage source, current source, and the three resistors are given. Then take a look at the circuit itself. You have two sources. That means you need to perform two analyses for any quantity that you need to find. The only quantity we need to find here is I2. Okay, the only quantity we need to find is I2. So we only need to analyze it twice. We don't need to find like VR1 or VR2 or VR3. We only need to find one quantity. So let's set this up. We need to analyze it twice, right? We need to analyze it once for VS, once for IS. So if we analyze once for VS, I'm going to note I2 as I2A. Okay, I2A. I2A. When I analyze it for IS active, I'm going to call it I2B. And the actual I2 is going to be a sum of I2A and I2B. Right? Make sense? So let's redraw the circuit diagram with only VS active. When only VS is active, we have, oh, also what I will do is, on the far right, I can see that R2 and R3 are in series. I'm going to write R4 is equal to R2 plus R3. So R4 is equal to 6 ohms. Just makes our job a little bit easier. Not that it was too difficult anyway, a little bit easier. Circuit's simple enough anyway. Okay, so setting up the problem, I'm reducing the two resistors on the far right, R2 and R3 in series. I'm going to call it R4. R4 has a value of R2 plus R3, 2 plus 4, 6 ohms. Is enough? Now, VS is active. IS, current source, is reduced to 0, means it's removed from the circuit, open circuit. What do we have? We have a voltage source, and you only have two resistors in the circuit. And that's it. You have I2A going down here. R1, R4. You have voltage, you have resistance. What technique comes to mind? Ohm's law. As easy as that. It's a one-step answer. So you can write I2A is simply equal to Vs or R1 plus R4. 10 divided by 11. This comes out to be 0.909 amps. It's a great illustration of how applying superposition can simplify your circuit, and you can have like a one-step answer. Okay, so take 10 seconds while you write it down, think over it, and let me know if you have any questions. Any questions at all? Make sense, right? And again, what analysis technique we use, or whatever technique that you choose, is up to you. Right here, it's quite evident that Ohm's law is the easiest thing, right? But in the next one, you will see you can use Ohm's law or you can use something else, and that something else will be. I'll let you tell me. When you have IS active, Vs is a short, and so Vs is a short, R1, R4, IS. What technique comes to mind? Current division. Absolutely. So when we redraw the circuit with only IS active, you have a current source, Vs is a short. Thus, R1, which is already connected to R4 in the current source at the top end, is now also connected at the bottom end to the other two. And when the two nodes are the same, everything's in parallel. IS comes down into the circuit and splits in two. One portion going into R1, other one going to R4. So you apply current division. But look at the direction of IS. Always follow the current directions and the reference polarities. IS is flowing down. So when we find the current going through R4, our reference direction originally given to us or asked of us in the problem is going down. It's opposite. So I2B is a fraction of IS. We can apply current division, find that value, but because it is the opposite direction, we put a minus sign in front of it. We put a minus sign in front of I2B. So I2B is now equal to, it's a fraction of IS. The fraction is given by REQ divided by R4. And because it's in the opposite direction, you put a minus in front. This is 2 amps. REQ is R1 in parallel with R4, which is 5 and 6. When you have two resistors in parallel, it's the product of the two divided by the sum of the two. So it's 30 divided by 11, which comes out to be 2.727 divided by 6. Anyone want to guess what the answer is? It's minus 0.909. And so you see why missing that reference direction of the current would be so crucial, would be so important. If I add up I2, I2 is I2A plus I2B as 0.909 plus minus 0.909. I2 is 0 amps. I2B. Sorry, what? Yes. Yep. Right here. If we missed the current direction and didn't have the minus sign, I would have 0.909 plus 0.909. My answer would be 1.98. It would be completely different. Or 1.81. Right? My answer would be completely different instead of being 0. So that's why it's important to take a look at the circuit diagram, take a look at the voltage polarities, take a look at the reference directions that are provided, and then proceed with your analysis. And again, as an engineer in your own fields, the same holds true. Always pay attention to the details. When companies put in their job descriptions, we want a detail-oriented candidate, this is something that they're referring to. They want to see how a candidate, meaning you all, when you go on your job interviews, pay attention to the minor details. So that's an example where that detail is important. All right, questions? Any questions? Does the procedure make sense? Does the analysis technique make sense? The setup of the problem, how we first redraw the circuit, we set it up for VS active, then we set it up for IS active. Once you redraw the circuit changes, you can analyze it in multiple ways. Here, you can choose to use Ohm's law again if you want to. You can reduce R1 and R4 down to one single resistance. You apply Ohm's law, find the voltage, then you apply Ohm's law again to find the current. Essentially, you're deriving the current division principle instead of applying the current division principle, right? But that's up to you. That's up to you. You can apply Ohm's law twice, or you can apply current division once, and you find the answer. So again, what technique you choose beyond the initial one, that's up to you. All right. Any questions? Okay. Well, consider the superposition homework assigned. We will now look at some basics for node voltages and mesh current analysis. So node voltage analysis homework, I believe, is due sometime in the next few days. That will be pushed back, and the superposition will be pulled forward. Okay, superposition is going to be moved forward. It's going to be moved ahead. Today is Wednesday. Superposition homework, I think, only has like 2 or 3 problems. 2 problems, I think, and some extra credit tutorials. Beyond that, it shouldn't. I mean, that 2 problems, it's not going to take you that long. But I will probably move it ahead to like Saturday or Sunday. And then node voltage analysis, mesh current analysis will be due sometime next week. So we will start with the basics of node voltage today, and then we'll look at the technique on Friday, and then the homework will be due sometime next week. Okay, so let's look at those basics. Node voltages and mesh currents. And some of this is, well, actually, most of it we have already discussed in the past, right? Node voltages and resistor voltages. But specifically, what we'll look at today is the relationship between resistor voltage in terms of the node voltages. Okay. So you look at the circuit diagram, and in the circuit diagram, you see there is one voltage source, Vs, right? There are 4 resistors, R1, R2, R3, R4. This is R3. And we are given the notations for the resistor voltages, V1, V2, V3, V4, and we are also given the polarities of those voltages. Okay. Now, when we get to the technique, node voltage analysis, you will not be given the polarity. You will choose the notation and you will choose the polarity. And you will choose the current direction. Okay, branch currents. In addition, here in this diagram, you see there are two currents, IA and IB, circular. Right? You can see they're moving clockwise inside that loop. Those are known as mesh currents right here. Mesh currents. These mesh currents are hypothetical. They do not exist. They are purely theoretical. They only exist as far as this analysis technique is concerned. And we will talk more about mesh currents when we get to MCA, mesh current analysis. Again, that won't be until next week. So we won't look at, or maybe Friday perhaps. We won't look at mesh currents until then. But suffice to say, they are hypothetical, they are theoretical in nature. They do not exist in real life beyond, beyond what we need for analysis. Okay, so let's look at the circuit. A is at the bottom, connected to ground. It is also our reference node. Right, so it's connected to ground. It is also our reference node. Reference node. Meaning all other node voltages are measured with respect to node A. When we say VB, VC, VD, the three nodes up top, B, C, and D, all of those nodes are connected with respect to ground. So VB is VBA, VC is VCA, VD is VDA. Right? Everybody's familiar with that concept, right? Then we look at nodes B and A. We see the voltage source VS is connected between B and A. Right? Voltage source Vs is connected between B and A. So it automatically means VB is equal to Vs. Automatically. The voltage at node B is equal to Vs because, and this is because Vs is between B and A. Right? Make sense? Just because A is a reference node. Does that make sense to everyone? This is an extremely important point. So if you have a voltage source connected in a circuit and you're doing node voltage analysis, if you choose one end of the source as your reference, the voltage for the node at the other end is automatically known. And that's a point that I will cover later on again. Anyway, so that was VB. Then we have VC and VD. If you want to describe the resistor voltages, V1, V2, V3, and V4 in terms of the node voltages, here's what we need to do. We take a look at the resistor. The resistor has two terminals, right? It has two terminals. The two terminals can be the two node voltages, right? You have two node voltages. So resistor is connected between two nodes. You can describe the resistor voltage because it's measured between the two nodes as the difference between the two nodes. You can write V1 is equal to the difference between B and C. And B is already given plus, C is already given as minus. And so you can write V1 is equal to VB minus VC. And that's the relationship that is described here in this table. V1 is VB minus VC. Similarly, you can write V2 is VC minus VA. But VA is already ground. And so this is equal to VC. Right? V2 is VC minus VA. VC is plus, VA is minus. And so VA is also ground, so we can write V2 is equal to VC. Does that make sense to everyone? You're describing the resistor voltages in terms of the node voltages. Yes.
Based on the polarity.
Absolutely. Absolutely. And absolutely correct. So the question being asked was, it's based on the polarity. And what if the polarity for V1 was flipped? So the polarity for V1 was flipped, then it would be VC minus VB. Right? Make sense to everyone? VC minus VB. Yes. So it doesn't matter what polarity you choose. Your answer will be correct. And we'll see that in the next slide. R1 is, well, R1 as a resistor does not have any polarity, right? It's a component. The voltage that appears across R1 will have polarity. But even if we choose, now logically, the current from Vs is going to go in this direction, right? For a source, it goes from low to high. So it's going in the upward direction. And so it goes around the circuit in this manner. And so it's entering R1 from the left. The current point of entry into the resistor will always be plus, point of exit will be minus. That would be the logical assumption to take or to make. Even if we choose V1 to be opposite, it's going to be the opposite for all equations in the circuit. So as long as you're consistent within your problem, your answer will always turn out to be correct, right? So V1 will be opposite polarity for the first equation, will be the opposite polarity for the second equation, the third equation, fourth equation, however many equations we write in the circuit, will be the opposite polarity for all equations. And so when we solve those equations, your final answer will always be correct. Well, no, does not matter which one we switch around, which one we're not. This is an assumption that we make at the beginning of the problem. Okay? And then we stick with those assumptions right till the end. So again, these assumptions are based on certain logic, right? As I said, current will only take one single pathway to go through. So it's going from minus to plus for the Vs, then it reaches up, it's making a right turn, it's going into R1 from the left. So the logical assumption to make is that R1 has a plus on the left and minus on the right. All I'm saying additionally to that statement is, even if we choose the polarity to be minus and plus this way, our answer will still be correct. Okay, that's all I'm adding to that statement. Does that make sense to everyone? Right. Okay, so this table basically lists the relationships between the resistor voltages and in terms of the node voltages. And how are we going to use these? Well, in this circuit right here, we have one single resistor which has current I flowing from left to right, and we have node voltages A and B, VA and VB. So if I apply Ohm's law, I can write I is equal to VR over R, right? From Ohm's law, I can write I is equal to VR over R. VR is basically the resistor voltage. That's all it means. VR is the resistor voltage divided by the resistor, you get I. Now I would express the resistor voltage in terms of the node voltages, VA and VB. I would write VR is VA minus VB, or I could write VB minus VA. But current direction is given to us. I is flowing from A to B. And if I is flowing from A to B, then VR is VA minus VB. So the assumption that you're going to make is the current direction. Node voltage analysis, again, we'll see this on Friday, requires you to make assumptions about the branch currents, meaning the current flowing through each individual resistor branch. And when you make that assumption, it doesn't matter which direction you choose, right? Because if the current is flowing from left to right and you write an equation for the first node, you're going to have the same exact direction for the second node and the third node, and so on and so forth. So when you add up all those equations together, it'll all work out. So here I can write I is VA minus VB divided by R. So we are expressing first the current in terms of the resistor voltage by applying Ohm's law. Then we express the resistor voltage in terms of the node voltages. And the two nodes are the ones where the resistor is connected. And which node is higher or which is lower is an assumption that you have to make. You have to choose, right? The assumption is based on the direction of the current, either going towards the right or going towards the left. So then if you take a look at this circuit, we apply KCL, and we apply KCL at node B. I have I1 entering the junction. I have I2 and I3 leaving the junction. Then I express each current in terms of Ohm's law. So each current by applying Ohm's law gives me VR1 divided by R1 is equal to VR2 divided by R2 plus VR3 divided by R3. And then I express each resistor voltage in terms of the node voltages for each individual resistor. And so I can write VR1 is equal to VA minus VB divided by R1, which is then equal to VR2, which is VB minus VC divided by R2, and VR3 is VB minus VD divided by R3. When we solve node voltage analysis, these will be given to you. R1, R2, R3 will be given to you. These are variables, VA, VB, VC, and VD. Basically X, Y, Z. You reduce the equation in the form of AX plus or minus BY plus or minus CY is equal to Z. You have a linear equation. You apply KCL at a different node, you get another linear equation. You keep on applying KCL, you generate a set of equations, then you solve it using any method you want, and you have your answers for VA, VB, VC, and VD. Simple math from that point on. But the important thing is how to generate those equations. And that's what we will learn in node voltage analysis and mesh current analysis. We will see that on Friday. For today, we'll end here. If you have any questions, I'm around for a few more minutes. Otherwise, have a good day. And look out for, keep an eye out for my email. But know for now that superposition will be due sometime this weekend. Again, it's only like 2 problems, so it should not take you that long. And we push back, yes.